Thank you very much, Max, for that very warm introduction. Thank you for all of your help organizing this. I do wonder if now that you know that this has been in the works for like 5 years, you're like, shouldn't this be a little better? No, so hopefully you are having a great time. I apologize to the core participants. This is, I think, the last time you'll be forced to listen to me speak. But hopefully you were intrigued by the title, Death and Dreams in Low Dimensions. We're going to talk today about culture. Culture is, of course, an essential part of the human experience. This is another image from Chauvet Cave. Judy showed one of these yesterday. Culture shapes our cognition. It structures our societies. A lot of the data in the so-called data deluge is cultural data. It's traces that are produced by human cultural activity. The song program is about intelligence, and I think you can make an argument that culture is also a very integral part of human intelligence. And I mean this in the sense that my friend and collaborator David Krakauer says, intelligent mechanisms help agents encode reality, make life more ordered, make the world a better one for living in, and give predictability, coherence, adaptability, and creativity to life. I think you could replace intelligent mechanisms with cultural things, and this entire argument would follow through. Now, you may be wondering what I really mean by culture. What is a good definition? Well, 75 years ago, roughly, the anthropologist Alfred Kroeber, father of Ursula K. Le Guin, and Kluckhorn tried to compile definitions of culture, and they came up with 164 distinct answers, which are contained in a book that is about this big in a sort of like little paperback edition. Obviously, we're not going to do that today. I'm just going to give you my preferred definition, which focuses not on the contents of culture, as in, sometimes people say, well, culture consists of beliefs and values and norms and institutions and practices. I'm going to give you a more sort of formal properties-focused definition. So this is my preferred definition. Culture is shared regularity in the organization of experience or the generation of action that's acquired through social life. And if you're interested in hearing the sort of whole version of this story, it's a paper I wrote a long time ago, Culture and Computation, Steps to a Probably Approximately Correct Theory of Culture, where I developed this definition, connect ideas in the sociological and anthropological literature about culture and cognition to some computational stuff, et cetera. For the students in the room, this is an example of something that I have done many times in my career, which was that I was very annoyed about something. In this case, I was very annoyed about the sort of vagueness with which ideas about culture were treated in a lot of social science literature, and so I decided to do something about it. This is me being angry that a dinosaur park has a, what everyone knows is a pelycosaur, not a dinosaur, a mammal-like reptile, in amongst the dinosaurs. It's very irritating. So how do we study culture? I mean, for many, many centuries, the kind of gold standard method, the primary approach was to do something humanistic, interpretive, very labor intensive. And these kinds of methods simply cannot scale with this deluge of cultural traces that we now have available. And so we have to turn to computational assistance to help us make sense of culture at scale. And what I want to focus on today are computational methods for studying textual traces, and in particular, in terms of the methodological side of the story, the way we're going to get to death and dreams, I'm going to focus on two fairly classic approaches, topic modeling and word embeddings, putting those two things together. Now, some of you might say, okay, I mean, topic modeling is 2 decades old, word embeddings is a decade old. Why, talk about these old school things? Well, these older techniques are more accessible in the sense that more people can use these tools with more limited computational resources. They're better understood. There's some rich theory that explains how and why they work. In many cases, they're foundational to new techniques. So a lot of what I'm going to tell you about, if you say, okay, for my application, I would want to use, embeddings, contextual embeddings derived from a transformer, whatever, totally fine. You could totally replace this modular part where we're going to use word embeddings with those things. And finally, I want to make the case that for many applications, they're actually more scientifically appropriate. And I'll tell you about the kinds of applications I'm thinking of in a little bit. So, OK, most of you are probably familiar with this, but for those who are not, the basic problem in topic modeling, which is something that certainly makes sense as an activity we want to do when confronting a lot of cultural data, is to figure out, like, what's going on in this cultural data? What are some of the main themes? What are the building blocks of that discourse? And which of those building blocks are used in a particular text? So the very classic approach to this is to view a document as a mixture over topics and a topic as a probability distribution over words. So, I mean, there's a wonderful Communications of the ACM article from 2012 that sort of illustrates this principle here. Here we have some scientific article. These are some topics learned from that corpus. You can see these are distribution, like this is a genetics topic, this is a evolution topic, a neuroscience topic, et cetera. And this document is created by picking those different topics with some distribution and sampling words from them. And that's, of course, what the plate notation, for those of you who read that, is expressing. Now, for a long time, when any kind of social scientist or digital humanist or anyone interested in dealing with large amounts of culture wanted to study text traces at scale, topic modeling was the main thing that people thought of. But about a decade ago, now everyone's like, word embeddings, or transformer-based things, or large language model type things. So what are word embeddings? Again, most people probably know, but this is essentially a method for representing units of text, whether you're talking about words in the case of word embeddings, or longer strings of text in the case of sentence embeddings, as vectors in some moderately high dimensional space. And we can think about word embeddings from a sort of social and cognitive science perspective. So my former student, Alina Arsenyev-Kohler, who's now on the faculty at Purdue, and I wrote a paper a few years ago called Machine Learning as a Model for Cultural Learning, where we kind of connect ideas in cognitive science and sociology about how cultural notions are represented and how they're acquired to some of these embedding type models. I'm not going to spend very much time talking about that today. What I'm instead going to give you a little bit of a discussion of is some work from the theory of machine learning done by Sanjeev Arora and his collaborators that really tried to give an explanation of how word embeddings work. It was, in fact, engaging with Sanjeev's ideas that kind of gave us all of the ingredients for developing the method that I'll tell you about today. All of these ideas sort of depart from this notion called the distributional hypothesis, the idea that when words appear in a similar context, they have some similarity in meaning. There is a strong version of this hypothesis that basically says the meaning of the word is the context in which it appears. But departing from this basic idea, a range of methods have been developed, most prominently these neural word embedding methods like word2vec, in which you take very simple architectures with a single hidden layer and give them either this task, given some context, guess the missing word, or the opposite of that task, given some word, guess the things that appear around it, and training a neural network, or I mean, there are other approaches like GLOVE, but basically trying to get good at this ends up producing these representations of words as vectors in reasonably high dimensional spaces, where the geometry of those vectors encodes semantically interesting things. So people were very excited when they observed that there were like directions in this space that seemed to correspond to gender or to verb tense or to certain kinds of like relations. Sociologists and other social scientists were really excited because we figured out that you could construct these latent dimensions. Like you could say, okay, let's find a general dimension in the space that corresponds to like class. This is my colleague James Evans' work, where you take a bunch of prototypes for two ends of like a class dimension, a very affluent versus a very poor end of the spectrum, and you can kind of learn a dimension, then project a bunch of words like golf is a very high-class sport, boxing is a very low-class sport, etc. And you could do all sorts of really cool things. Gender was a very popular thing to study. This is, Alina and I validated a gender dimension. We extracted from a bunch of New York Times articles. And then you could use this to study, say, how concepts relating to like body size and obesity are gendered. So like burly is a very male connoting word, whereas like anorexic is a very female connoting word. Because I'm very proud of Alina and like to advertise her work, you can even learn dimensions for things like how judgmental people are about diseases. And here you can see people are the least judgmental about chronic diseases and the most judgmental about behavioral diseases. So people have used these basic methods to do all sorts of really cool things to understand like how cultural understandings of disease and the stigma attached to them evolves over time, etc. So from a sort of social science and cognitive science perspective, you can think of word embeddings as kind of operationalizing the content of schemata, kind of hierarchically nested building blocks of our cognition at both word level and kind of lower level, like these kind of dimensional things, and use it as very simplified models of our processes of learning and modifying and deploying these schemata. But how does all of this actually work? Why can we learn these high dimensional, reasonably high dimensional, like 300 dimensional vectors that encode this kind of semantic information? So this was the thing that Sanjeev and his collaborators set out to explain, and it was reading these papers. It was, Alina and I really wanted to make sure that we understood how these techniques were doing all these amazing things. That was what led us to this method that I'm going to mostly tell you about today. So I like to say this as like how reading theoretical machine learning can change your life, because it really was amazing for all of us on this particular collaboration team. Above all, again, I want to highlight Alina and my colleagues Vicky Mays, Susan Cochran, and Kaiwei Chang. And the work I'm going to tell you about right now came out in PNAS a couple of years ago. Okay, so here's the basic Aurora picture. Imagine you have already some semantic space, which lives in, say, 300 dimensions. Each word is represented by a vector in that 300-dimensional space. And what I want you to imagine is that we have a special vector, what we'll call a discourse vector, that determines kind of what we're talking about at the time. To make that more concrete, what the discourse vector does is the probability of a particular word being emitted at time t conditioned on a position of the discourse vector, c sub t, is just going to be proportional to the exponential of the inner product of wherever that discourse vector is and that particular word's vector, right? This is a simple log linear topic model. So words whose vectors are very close to the discourse vector will have high probability. Those that are far away will have low probability. And again, just to emphasize, this discourse vector is defining a topic in the sense of topic modeling, right? Wherever the discourse vector is, we now have a probability distribution over words. So recall then that in topic modeling, a document is a mixture of topic, a topic is a distribution over words. Just with this basic model, we have a way of actually an infinite number of possible topics for all of the possible positions of that discourse vector. Okay, now in the Aurora et al. Sort of simplest version of this generative model, that discourse vector does a random walk in this high dimensional space, and step by step it generates words according to whatever topic model is defined based on where the discourse vector is pointing. And what Sanjeev and his colleagues showed is that if you have that generative model, that will produce text such that if you train a word embedding on that text, it will have all of these very nice features. So this paper, which I will not go into any of the details of, essentially like explains this relationship. Well, what does this get us? I mean, among other things, it gives you a very simple recipe and actually explains a procedure that people had been using for connecting text to the maximum a posteriori estimate of wherever the discourse vector is. You just take a strip of words, in the simplest case, average their word vectors together, and that is, under this generative model, you're just inverting the generative model, the MAP of the discourse vector position. So if you slide these windows along, you're just getting different estimates of where the discourse vector is. Now, we actually do something slightly more complicated, which I'll explain in a second. But one of the things I wanted to point out is I very much had the same dream as we were working with these models that Robert Hawkins talked about, that like, wouldn't it be amazing if we could figure out what the kind of vector field is, right? This picture that, we've just got this random walking discourse vector, I mean, is obviously a gross, mathematically convenient approximation. What we'd actually like to know is like what the structure of that kind of, stochastic dynamical system looks like. Maybe this is something that, folks who are interested in those things could think about. But in any case, I told you we use something slightly more complicated. The slightly more complicated thing we did involves changing both the generative model and then how you actually infer the discourse vector position. This is the smooth inverse frequency approach that Sanjeev and different constellation of collaborators developed. And it basically says, okay, rather than having this simple log linear topic model where the probability of a word appearing at a particular point in the text is dictated exclusively by the discourse vector, in this case, we, with some probability alpha, pick words just based on word frequency, and with probability 1 minus alpha, pick it according to this topic model. Even this topic model is slightly more complicated because we have both a kind of global component of the discourse vector, which is capturing sort of what a body of discourse is generically about, and then we have this kind of local discourse vector that moves around. And so under this picture, the MAP estimate of where that combined global plus local discourse vector is just slightly more complicated. You now weight words in a way that depends inversely on their frequency. So you're down weighting frequent words. You're compared to rarer words, the idea being that they're less informative. And once you have this, the sort of details of the procedure are you simply take a whole bunch of these estimates, combine them together, PCA, take the largest principal component, project things onto that, subtract that off, and then that gives you your estimate of what the local discourse vector is doing. Okay, so now we have a very, very simple model that you could say describes both the generation in the sort of forward version and understanding in the inference side of linguistic data. But this also suggests a new way of thinking about topic modeling, where topics are still distributions over words, but now instead of viewing a document as a mixture of topics, you view it as a trajectory through semantic space. I mean, which is, of course, like actually what happens in contextual embeddings and transformer type things. Now, here we're still in a high dimensional space. So, okay, it would be nice to simplify things further. And one way to simplify those things is basically to take that space of word embeddings and do sparse dictionary learning. So what we're wanting to do here is write every word vector as a sparse linear combination of kind of building blocks of meanings, what we call atoms or discourse atoms, so that you're trying to do as good a job as possible, right, of approximating the full embedding matrix as the product of this topic matrix and a sparse coefficient matrix. So we're just trying to minimize, or to find the d and x that minimizes this difference between the reconstructed matrix and the original matrix in a Frobenius norm sense, subject to a sparsity constraint that is in reality always saturated. And the way that you do this is just by alternating in the approach we use, k singular value decomposition, updates to the sparse coefficient matrix, which uses something called orthogonal matching pursuit, and updates to the matrix of topics, which uses SVD many times. If you want I will just say the literature on this is both spread out and very confusingly written. So in the appendix, I viewed this as a small service we could do to the community. I worked very hard on writing an extremely self-contained, like 1.5-page exposition of this. So you may want to read this. Thank you to the authors of the original papers, but try to crystallize it down. OK, so now that we've got this decomposition, we can use this correspondence that says any discourse vector, any position in the embedding space defines a topic model. Well, then each atom of meaning defines a topic model, and those atoms allow us to understand the content of the embedding space. You can think of it as a kind of compression or sparse coding of the semantic content of the embedding space. So I'm going to tell you about our first application, which was something called the National Violent Death Reporting System. This is a CDC-maintained database that over time has expanded to include every state in the US. And these are records of so-called violent deaths, deaths by homicide, deaths by suicide, homicide, suicide, and what I think you could describe as like spectacular accidents. So like, think of the kind of accidents you'd read about where you're like, oh my God, those kinds of accidents. I do have to warn you, I mean, there will be some talk about things having to do with homicide and suicide, so just be forewarned. These records are interesting because there are a bunch of structured variables that describe the death, but there are also these narratives. These narratives are produced by public health workers using records that are produced by law enforcement and medical examiners. And they're just attempts to make sense of the death. Like, this particular death, what's the kind of story? And so we took all of these narratives, trained word embeddings on them, and then discretized the space, or did sparse dictionary learning on the space, and got these atoms. And I mean, what is very interesting is if you look, these are just some sample topics within these narratives. They're very easy to interpret. And so like this one has to do with physical aggression. This one is describing how clean or messy a space is. There are these very poignant topics that describe people basically being like, everything seemed fine. How could this, you can see how the folks these show up in suicides often, how the folks who are left behind are trying to make sense of what happened, et cetera. So, okay, now we know what the content of this space is, so we can go a bit further. These atoms allow us to do a kind of Voronoi tessellation of the embedding space to break it up into regions where, like, this region is sort of mostly, or this region is close to this atom, this region is close to this atom. So we can kind of coarse grain the narratives into sequences of these atoms. We just take a sliding window of text, MAP estimate the discourse vector, find the atom that's closest to it, and so now we've turned the narrative from a sequence of words into a sequence of topics. And so this immediately allows us to do interesting things like, well, okay, here are narratives divided by manner of death undetermined suicide, unintentional homicide, and legal intervention, which is the euphemism that is used for police killings and other deaths that occur in the context of the legal system. We can, basically say, okay, well, what is the kind of fraction of narratives that have these different topics, represent the groups of narratives in that way, and then just cluster, and the kinds of things we find make sense. Homicide and legal intervention death cluster, that makes sense because legal intervention deaths are homicides where the killing is done by someone in the justice system. Undetermined deaths and suicides cluster together. That also makes sense because most undetermined deaths are suicides where there just isn't enough evidence to make that determination, etc. So what can you do with our method that you can't do with kind of normal topic modeling? I mean, the first thing to emphasize again is that the topics we get are very sharp. That's because they're trying to do a different job than kind of traditional latent Dirichlet allocation type methods. These are topics that my colleague James Evans found with his colleague. This is an illustration from like a book that they're working on, where these are some discourse atoms they found. Again, you can see they're like very semantically tight. You can also do the same trick that I described of like learning latent dimensions. And because these topics live in embedding space, right? They're just vectors in the semantic space. You can project those atoms onto these dimensions and figure out how gendered they are or how classed they are, et cetera. So we learned gender dimensions, and this is an interesting case where we have the sort of semantic gender of a whole bunch of topics. In other words, how much that topic projects onto the sort of male versus female end of the spectrum. We also have the gender prevalence ratio, the ratio of male to female or female to male decedents in which that topic shows up. And you can see these things are highly correlated. And if we look at the sort of two ends of the spectrum, they make sense. This is the very male end. This is the very female end. If we look, for example, at methods of death, this is the most masculine method of death. If you do not know, these are all names of various long guns and shotguns. The firearm mortality rate is 6 times higher for men than for women. And again, if you don't know, these are names of sedatives and pain medication, and women are more likely to use to commit suicide by poisoning. So these kinds of things really kind of make sense in terms of what we're seeing. Now, you might say, okay, but what have we really learned? I already told you that we know the gender of the decedents. They're present in the structured variable. Couldn't we have gotten all of that just from like these prevalence information? But you can do the same trick for any contrast, although you have to make sure that the dimension like makes sense. Some dimensions are harder to learn than others reliably. So we thought, okay, well, what about indoors versus outdoors? Okay, so we just make this dimension that corresponds to how indoor or outdoor the topic is. The most indoor topic has to do with fumes. You can sort of picture how people are dying in this situation. The most outdoor topic are outdoor locations. I mean, in some cases, these are like firearm deaths, hunting accidents, this sort of thing. Okay, so these techniques you can use to understand any kind of domain-specific discourse. And what I really mean here is you have a corpus where there is a vocabulary that's used in a specialized way. Like there is definitely a specific discourse to these NVDRS records, and in lots of different kind of use cases in the humanities and social sciences, this is going to be sort of typical. You have a bounded domain of discourse where language is used in a specific fashion. We use these methods to study legal intervention deaths and racial bias, to study gender and mental health. These are both using NVDRS data, where here we found, among other things, that men have sort of different manifestations of mental health issues, many of which are not actually used in sort of official diagnostic criteria, which strongly suggests that there's a lot of undiagnosed mental health issues with a gender bias that sort of disfavors men. We've used this to study interview, talk about family and the role of family in people's life, dreams, which we'll talk about in a moment, and I know there are other folks who are applying these methods to new problems. But again, to kind of do my little sales pitch for this, these methods, these simpler methods, are more data efficient, right? So you can get high quality embeddings on much smaller corpora. The math from the data to results are kind of fully mapped out by this kind of theory. You're not needing to trust that what other fine tuning or in context learning you're doing has like fully suppressed whatever is going on in the much larger corpus that the model was originally trained on, and you're really seeing stuff that is only in the corpus that you're interested in. You can just work only with that corpus, and and this is something we've been struggling with in our own work. If you want to be really, you have sensitive data that you can't be, sending through some API, like you're going to have to set up your own large language model locally, blah, blah, blah. These things, you just don't have those concerns because you can just do it on your laptop. Yes, Rich?
When you say learning a dimension, does that always mean you're finding a particular direction to project onto?
Yes. Yes. Yes, yes, and you're doing a human, there's a big human role in this because you have to decide how to anchor the dimension and like check that it makes sense, et cetera. But yes, I think the motivating picture is, you're saying, okay, the actual kind of ambient dimensions of this embedding space have no semantic meaning whatsoever, but like, okay, there's some way that you could transform, probably not all 300 dimensions, but like some number of the dimensions, right, there are directions in that space that have a semantic interpretation. Yes?
Very sympathetic to your idea about, the benefits of this. Something that we did a couple of years ago was actually focusing on the temporal dynamics of how these things change based on memory principles of what gets reinforced, etc. So I wanted to ask, in what you've shown us, it's all been kind of static.
Yep.
How would you consider the temporal dynamics of it?
Yeah, that's a very difficult question. As I'm sure you know, like people do these things where they like try to temporally align embeddings. I am very suspicious of that, basically because, again, I worry that whatever procedure you're doing to do the temporal alignment is possibly introducing some structure that you're like, oh, look, it's there. And I'm like, yeah, because you align the, yeah. So I think probably the safest way to do something like that, from my perspective, again, if we're sticking at this very technically simple-minded level, is, to chunk your corpus temporally and then use methods like, looking at these discourse atoms and projections onto them where, what you have to do is try to like align the atoms over time, like say like this seems to be, and I should just say as a sidebar, like if you do the KSVD procedure lots of times, like there will be some variability in the atoms that show up because obviously, we're heuristically doing that optimization problem. There are lots of things that are very robust across them. So I would look for like, okay, is there robust like gender dimensions plus topics or whatever over time that seem to largely overlap in their semantic content, but like do those sorts of things where you're kind of allowing your coordinate systems to kind of drift naturally as a function of like the semantic content of the space, and you're just projecting things onto those targets.
So great point. I was more thinking an arrow in space-time of which, in a kind of a predictive way, we could see which direction.
Oh, I see. Okay. sorry, I misunderstood. Yeah, so I mean, people have done things like that. So like my student Bernie did a very interesting paper where, you know, you can, with like a certain number of samples of like some trajectory, try to like predict it, where it's gonna go. Again, you know, you have to sort of deal with this issue of what's staying still versus what's moving, but yeah. Okay, I'm gonna talk about dreams. Understanding dreams. This was a project that started last year at the Diverse Intelligences Summer Institute. Want to acknowledge this very interdisciplinary team. I dubbed them the Dream Team. You know, Anya is a psychiatrist. Mason is a psychologist. Jess and Sophia are philosophers who are interested in, you know, phenomenology and memory and this sort of thing. And above all, I want to acknowledge Luke, who all of you know, who, despite what you're about to hear about, is an ant biologist by training, but like, you know, talk about far transfer, did an amazing job leading this project. So why study dreams? I mean, dreams have played a really important role in lots of different, I mean, you could say the same thing that I said about culture, about dreams. I mean, just to give a few examples, this is Parmenides over there on the far right, the so-called father of logic. Parmenides was also what's called an iatromantus, a sort of doctor prophet, and his, not only is his like main text a kind of account of a sort of dream experience, Parmenides' main job was to lead a practice called dream incubation, which is a thing that they did in the Hellenic world, where you would like basically go hibernate in a cave to try to get answers to questions, heal, et cetera, et cetera. Aristotle provided possibly the first, at least again, in the Hellenic tradition, naturalistic account of dreams, not given by gods, but kind of coming from natural causes. There is a lot of interest in dreams and dream interpretation. Cicero wrote a famous text called The Dream of Scipio. This is a figure of commentary on that dream by an author named Macrobius that was very sort of foundational in thinking about dream interpretation and its collection to philosophy. This is an example of dream interpretation in the context of the Buddhist world. So this is an illustration of Svapna Darshana Yoga, or dream yoga. And then in the Islamic and Islamicate world, this is also a very important thing, this practice of tahbir al-ruya, or you know, dream interpretation. There were tons of texts like this, some of them drawing on translations of Hellenic text and then elaborating and developing it. The point is, like, dreams have played a really important role in lots and lots of different cultures for millennia. More recently, the sort of foundational work on psychoanalysis by Sigmund Freud and Carl Jung, obviously dreams played a really major role, but this is not just an old thing. Now, there are lots of folks who believe that dreams are indicators of mental and physical health. If you look at things like nightmares or lucid dreams or other kind of dream-related conditions, parasomnia or sleep-related conditions, they have distinct physiological signals. Disorders affecting REM sleep, like REM sleep disorders or narcolepsy or PTSD, often are associated with particular kinds of dream content. Insomniac dreams have particular kind of content. In other words, you know, there's a lot of evidence that both the affective and semantic content of dreams are actually closely coupled to each other and to the kinds of experiences that people had. So in order to study these dreams, we used a data source called DreamBank, which spanning, it's you know, more than a century, 1897 to 2011. This is a heterogeneous corpus where you've put together lots of different sources. Some are longitudinal, like lots of descriptions of one dream, or of dreams from one person. Some of them are cohort, slice of time, a bunch of California high school kids, their dreams, wide range of age, 70 to 74. A lot of variability in length, but the sort of average account is like reasonably long. We use the full corpus to train the embeddings. We remove short reports when we're doing this like SIF embedding stuff. And then we remove unusual sources for the analyses I'm about to show you. The unusual sources are blind patients, because that obviously might have something to do with the kind of dreams they report, a single pedophile, and Vietnam veterans. So those are taken out. And so we do the same trick. We take the text, train word embeddings, find the atoms, and now, okay, remember we can do the same thing. We've got all these atoms. They're living in this semantic space. We can find dimensions. In this case, the dimensions we're going to be interested in are kind of affective dimensions, which we break down into valence, like how positive or negative the thing is. Is it like happy or sad? And arousal, how like, you know, is it kind of low-key or very agitated? And so these are the anchor words for the valence dimension and the arousal dimension. And these are kind of driven by various, what does this sound? Like insights from the literature to kind of figure out what these anchor words should be. Okay, so the first thing I want to tell you is that the arousal and valence of topics are uncorrelated. So each of these dots represents a topic, like grammatical structure, negative emotion, dream characters, in a valence by arousal space. They're unrelated to each other. However, if we do the same trick of taking windows of text, MAP estimating the discourse vector, finding the nearest atom, giving those atoms all valence and arousal, and then say computing the median valence and arousal of each dream, dream arousal at the whole dream level decreases with valence. What that's saying is that high arousal dreams tend to have negative valence. These are like, I'm running around trying to find a bathroom and I'm very agitated and whatever, whereas high valence dreams tend to be somewhat lower arousal. We're sitting there having a good time listening to a talk. One of the other things we find is that the kind of, as we found with the death narratives and so on, the affective content of dreams is coupled to their semantic content. So these heat maps show these are the top quartile and bottom quartile of valence, the top quartile and bottom quartile of arousal, just the sort of proportions with which these different topics show up. You can see, interestingly, that there is like quite a lot of similarity between low valence and high arousal dreams, but also that these are different from one another. I mean, they are statistically different from one another. To kind of get a sense of what's going on, you can look at topics that have sort of maximum difference between their prevalence in the high valence and low valence quartiles and the low arousal, high arousal, low arousal, and like, okay, again, it makes sense. Things that show up in like very negatively valenced dreams are like didn't want, some physical actions, abrupt actions. Things that show up in like very positive are like things having to do with fun sports stuff, things having to do with specific characters, human interaction, etc. Okay, so there does seem to be this real variability of semantic content with affective content. We also were able to replicate the findings from a really classic study on dreams by Hall and Van de Kassel, looking at basically gender differences in the content of dreams. This is from 1966. They found that the dreams of women contain more emotion content, social interaction, and female dream characters. Male dreams have more physical aggression and are more often set outdoors. Here you look at differences in prevalence. And lo and behold, like outside movement, environmental features, movement with another, those are all very male features. Dream characters, emotions like shock and concern, relationships are very prevalent topics in female dreams. So we replicate that basic finding. Now, so far I've only been telling you about these kind of basic patterns. Can we do something to talk about structure? So we use networks to represent the semantic structure of dreams, and we do this in the following fashion. We've now got these sequence of topics. In a lot of cases, the topic is sort of staying the same. Whenever there is a transition, we put an edge between those topics. So here's an example of a dream where someone is dreaming that they're sitting at home, an alien comes in, they go to get a baseball bat, wake up their brother, but they end up getting shot by the alien. This is a network that corresponds to that sequence of topics that are being visited. Those dream networks generally have kind of small world features. So compared to random networks with the same degree distribution, they tend to have shorter paths, higher clustering coefficient. That is like more situations where you have like closed triangles. They're individually kind of Poisson, but if you take the union of all of those dream networks and look at the degree distribution in that sense, there are some nodes, which are individual topics in specific dreams, that have actually lots of, have very high degree. So you might ask yourself, okay, well, given these dream networks, like if I'm in a, say, happy topic, am I most likely to transition to or be transitioned from another happy topic? And same thing with arousal. And we find that that's true. If you look at the valence of a topic and the mean valence of its neighbors, both of those things are highly correlated. Neighboring topics tend to have similar valence and arousal. Now you can ask yourself the question of whether dreams are semantically coherent. Now what I mean by semantically coherent is, well, there's previous work that suggests that like if you have dreams where the words are like very dissimilar, you could think of this as like, you know, the cosine similarity between those word vectors is like negative. Those are interpreted by people as incoherent. So to measure semantic coherence, we just look at like, you know, the cosine similarity of the topics as we're going link by link. Now, it is the case that incoherence kind of has multiple meanings. Is that a bird that hit the window? Hmm?
Some sort of cone fell.
Oh, I see. Interesting. Okay. Thank goodness. Incoherence. That was a good example of incoherence. I was talking about cosine similarity, and then it's like, is that a bird? That is associated with disorganized thought, as is found in schizophrenia, but it's also associated with narrative progression and creativity. And so the overall answer is that dreams, if we look at the kind of, you know, an individual dream network, we're going to use longer links to represent things that have lower cosine similarity. Dreams are typically semantically coherent on average. So dreams tend to be composed of coherent semantic connections, but there is still variability. And again, that variability in the semantic coherence is associated with the affective content of the dreams. So here in these plots, you're looking at top valence and bottom valence dreams, top arousal and bottom arousal dreams by quartile, and looking at the mean coherence, and then the standard deviation in the coherence, which is basically saying like, are you coherent on average, and how much variability is there in the sort of local coherence of the dream? And the TLDR of this is that high valence and low arousal dreams are a kind of mixture of regions of semantic coherence and then these transitions. So you have kind of topic shifts between relatively coherent regions. Low valence and high arousal dreams are less coherent overall and tend to have greater persistence on particular regions. Okay, so can we really broadly characterize the relationship between affect and structure? I mean, is there a way that you could say, what are the structural features of these two dream networks, and like, is this a positive dream or negative dream? Who, can I just show of hands? Positive dream. Who thinks this is a positive dream? Who thinks this is a negative dream? And who is still dreaming? How about this? Negative dream, positive dream. OK, people were better on that one. All right, so we take a whole bunch of different network features, which I just put these up there so you can look at the slides and figure out what they are. But they're all the kinds of things that if you know anything about network science would like totally make sense. And then we do something called partial least squares, because these different features have a lot of collinearity. This is a procedure that's kind of regression-y. And what we find when we do this PLS onto valence and arousal is we're able to describe the kinds of features that high valence dreams and low valence dreams have, and high arousal dreams and low arousal dreams. So high valence dreams are more modular and linear. Low valence dreams have more kind of loopy things where you're like going back and forth between topics, and more dominant, typically negative topics. High arousal dreams tend to be larger. They have more of these, again, dominant, typically negative topics. Low arousal dreams have more of these sort of loops. So now, is this a positive or negative dream? This is a positive dream, right? It's like very kind of linear and structured. This is a negative dream, lots of loops, some dominant topics, et cetera. Here are the networks for some typical negative dreams, along with kind of their percentiles on a bunch of these different characteristics. I'll just give you an example of one negative dream. We won't sit here and read this because I'm almost out of time, but this is basically like a sort of ghost story type situation where this spirit-like woman is kind of appearing and disappearing. They're in a building. You know, she keeps on saying the word Tarkington, et cetera. You know, people are floating into, I mean, this is a very weird dream kind of going all over the place. Here are some typical positive dreams. This one that we've been looking at is very simple. You're riding in a car with somebody's boyfriend. Somebody is in the backseat eating a chocolate donut. He gives you a bite, hooray. He looks good and healthy, everyone is happy. Yeah, see, that's a great, wonderful, very linear, makes a lot of sense. You can see it also has those little topic shifts. Okay, so yeah, this is the kind of thing we tend to see in positive dreams. Okay, this is much too complicated to explain, so I'll just give you again the TLDR. The most common topics in low valence and high arousal dreams are more structurally dominant than the most common topics in high valence and low arousal dreams. This you could interpret as sort of a fixation kind of thing. Okay, I will also just mention all of these findings, like we, and by we I really mean Luke, like kicked the tires on this to the max. So, you know, it's robust to the number of atoms. It's robust you look at this very homogeneous subcorpus that we had analyzed earlier on the gender questions. It's robust if you use a different thing to analyze sentiment. So with the number of topics we use, there's a very high correlation in the coefficients that you find for the different things. They all point in the same direction. If you, instead of doing PLS, do a different regression thing that allows you to control for source, things are very robust, et cetera. So, okay, wrapping up, understanding dreams is actually connected to like a very rich and interesting literature. So there are anecdotal studies that say that like negative affect is associated with fragmentation of memory. It's also associated with like low memory for a context, for reduced ability to form associations. Positive affect sort of works the opposite way. All these kind of findings in different contexts about memory make sense in terms of what we're finding with dreams. We think there's lots of potential to integrate this in clinical settings. So, you know, if you combine these methods with records of dreams produced in sleep studies, you could obviously see what's going on in the brain with brain activity and other physiological markers. You could use it to study lucid dreams, REM disorders, It's also probably helpful or potentially helpful for identifying psychopathology. So we told you there are all these associations of like disorder and structural characteristics and various psychiatric conditions like reduced coherence. It might give you a new way to look at the degree of rumination. More broadly, one of the reasons we were really interested in this is its potential as a tool to understand all sorts of these like altered experiences. So whether you're talking about like psychedelic experiences or experiences of pure consciousness, there are like large records of people's like meditation reports, near-death experiences, any of these kind of subjective self-report kind of accounts of people's texture of experience. These methods allow us to study those specific, like domain-specific language corpora at scale. And I think overall, my hope is that this will give us a tool to kind of do phenomenology, like to look at people's lived experience, the texture of those experiences in detail, whether ordinary experience or altered experience at large scale. And so that's what I'm really excited about. I want to thank the folks who funded various parts of this. Also, for the people who are here, if you would like to hear about metalheads and evolution, just let me know. I have like a little spiel I can do on cultural evolutionary methods, studying the evolution of metal music, which is super cool, which obviously I don't have time to do. But if you're interested in this, let me know, and thanks.